because we're a little bit short on time, we're on a tight schedule, I'm gonna cut it there, but I'll also tweet this link. This was another link from Kevin Murphy, or from Kevin Ward, that he shared with us to help us start our plenaries. So with that, I will share my screen again with the slides and hand it over to Tamara Ledley, ESIP's president.
Okay, good morning, everyone. For those of you who don't know me yet, I am Tamara Ledley, ESIP's president. So one way that the ESIP community aligns its efforts is through a shared agenda reflected by high-level themes. Each year we focus on one of those themes and orient the ESIP meeting plenaries, the sessions, ongoing webinar series, and other initiatives spurred by ESIP's collaboration areas and members to that theme. Later in this plenary, we'll do a bit of crowdsourcing work together to gather community input on our high-level themes for the next 5 years. This year's theme, which it is likely you've heard us mention over the past few days, is putting data to work, which sums up the themes over the past 5 years. This theme has a double meaning. The first focus is on showcasing the interesting ways that earth science data is being used. The last 2 days have had an abundance of examples, but one area that I dedicated time to was the teacher workshop. There we had teachers working with data, visualizations, and models to explore current and projected environmental conditions and the impact of climate solutions on the Earth system. The tools included NOAA's Climate Explorer, En-ROADS, a climate solutions decision support model, My NASA Data, and Science on a Sphere Mobile Explorer. The other interpretation encompasses how we build public-private partnerships. Following the winter meeting, Krista Staub and Carl Benedict created a public-private partnership ESIP cluster, which had a session on Tuesday. Some of our plenary speakers next week will also highlight this aspect of the theme. Now I'll turn the floor over to Annie Burgess, ESIP's lab director, who will introduce our first plenary speaker.
Thanks, Tamara. Can everyone hear me okay? Tamara, can you hear me?
Yes, I can hear you.
Okay,
yes, we
great.
can hear you.
All right, wonderful. Well, good morning, everyone. And I am very happy to be the one to introduce my friend Sheldon Timin. Shell is a physical oceanographer who has worked for over 25 years on the retrieval of ocean temperature from space. And I'd say is a bona fide expert in that field. She started out at MIT for her bachelor's, then headed to Scripps for her master's in physical oceanography, and finished at the University of Miami with her PhD in meteorology and physical oceanography. She has served on numerous scientific committees and is most notably chair of a standing committee for the National Academy of Sciences. Most recently, Shell has turned her focus to more interdisciplinary pursuits, concentrating on things like air-sea fluxes, biophysical interactions, and upper ocean physical processes, all the while becoming a crack Python programmer and advocate for cloud computing, open source software, and inclusivity in science. So I am super excited to have Shell here this morning, and I would like to turn it over to her. Welcome, Shell.
Thanks, Annie. Let me figure out how to share my screen. Okay, is everyone seeing my screen now?
Yes.
All right. So thank you. Thanks for that nice introduction, Annie. I'm Shel Timin, and I'm really honored to be talking at ESIP because I see how ESIP strengthens the connections between data, technologies, and science, and really works to empower transformational science. And it's not just about technology, and I think that's what ESIP gets. It's also about building a community together. So I think I understand about how important community is because I was in a really toxic work environment for years. And I knew that if I left, I'd lose access to data, software, and computer resources. 18 years of software that I had built for doing my science. But then I left. And I lost everything, I thought. My worst fears had come true, and I had to decide my future path. Would I continue to do the same sort of fearful science, or would I risk trying something different? So I started weekend Python classes. I participated in hackathons. I joined Twitter, and I really began to understand the power of an open science community, because that was the one thing that I didn't lose my community, and they helped me get through this transition period. And instead of doors closing, which is what I had feared, doors really started opening all around me. And this has been an amazing source of growth for me. And it's one that I believe in so strongly that I want to share and help grow this community. And it brings me to where I am today to tell a story about empowering transformational science. Communities build open science, and open science is more efficient, and efficient science leads to transformational results. And why is that? Because what technical factors influence the velocity of science, how fast we can accomplish science and move on to the next result? Well, data, software, and compute, I think we all know those are an integral part of science, and they can either act to impede and slow down, or they can accelerate and speed up progress in science. There are studies that show there's this 80-20 rule for research, and it seems pretty universal. 80% of our time, and I can say this is true for me as well, is really spent accessing and organizing data and running analyses. And there's really about 20% time for actually analyzing results and doing the interpretation, the science part of it that's going to advance our field. So how do we change that ratio? And how do we flip that relationship? And this is really important work. And I think this is where ESIP comes in. By expanding that 20%, we free up time for scientists to think and build connections between the different threads of science, weaving together different data sets, drawing conclusions. This is where big ideas come from. And these are the ideas that can change and advance how we think about Earth system science. Most of us are aware of the enormous data volumes that will be created by future satellites. And a lot of us, especially people in this room, have been looking forward and realizing that our current scientific workflow that requires downloading data is going to have to change. I think that we're already at that point where access to data is impeding progress. Right now, we have new climate model projections, like the CMIP-6, which is in the upper right-hand corner. This has over 500 terabytes of data. There's a multi-scale, ultra-high resolution sea surface temperature data set. This is the most popular data set at NASA's Physical Oceanographic Data Archive for accessing small bits of the data. But it's not even in the top 10 for downloading because of its size. And you really need a full data set to do the type of spatial temporal analyses that are going to advance how we understand air-sea interactions. These data have now been put into the cloud for storage. And scientists can now bring their ideas and their analyses to the data, removing the barrier of having to download the data first. A friend just told me that he wrote a proposal with 4 months of time allocated to just download and organize the CMIP-6 data. They just got that time back because now that data is on the cloud and they're moving their compute to the data, freeing up those 4 months of time, which is a lot of time to actually think about the results. So analytics optimized data store, it just flows off the tongue, I know. So AODs are the stuff that sort of scientists dream about, or at least I do. Currently, most of the data that I get are in Netcdf files, which are a wonderful format. a substantial advantage over our old way of exchanging data, which was pretty much binary with no metadata. But these are organized so that a single file can be read into a computer's RAM storage. They're organized by days, by months, by years, depending on the file size. And here there are several new AODSs, and here I'm just going to talk about ZAR because that's the one I'm most familiar about. But ZAR, it works to make large data sets easily accessible for distributed computing. And these are both locally and cloud-based computing. So these advances in data formats, they work synergistically with advances in open source software libraries. And lazy loading is another important advance. This is basically you delay reading until it's needed for compute. So you load the data set in, but it really only loads the metadata, just the part that it needs to know about what data, where it is, that the part that you want to access. So everything's delayed until you need it for compute, and then only the bits of data that you need are loaded for that calculation. And modern open source libraries incorporate lazy loading, parallel computing, and optimize access easily. And I'm going to introduce those in a minute. But first, I wanted to talk about what does a data store look like? Because I think this was really interesting to me. On the left side, many of us are quite familiar with the Netcdf data format. And like I said, you know, the directory structure is probably organized into years, months, or days that then have their corresponding files in that directory. And it all sort of makes sense. And it's how we've gotten used to doing science, and it's how many of us were trained to do science. The new ZAR format is just a JSON file that contains the metadata for each variable, and the file names are, as you can see, they're like 0.0, they're meaningless. And that's okay, because you don't access file names, you just access the data. It's invisible to you what format it's stored in. And I think, to me, this was really striking because I was trained to think about days and months and years and how I would be running my analyses. And it really shapes what sort of questions I think I can ask of a different data set and how I feel like I'm going to ask it. With these new formats, you're just accessing the data. You don't care so much about the structure of how that data set is formed. And I think it opens up a new type of scientific question that you can ask, and it allows your brain to think in different ways. And one of the most important things is that what you really want to know is that it's lightning fast. And here's an example. So here I'm accessing data using Netcdf and ZAR. So the two different formats side by side. This is a 400 gigabyte data set that I'm accessing. And to access it and this is just on my local computer at this point. So to access it in Netcdf, I create a list of file names and then I access the data. This took 13 minutes, mostly because it was still lazy loading it, but Netcdf has the metadata sprinkled throughout each file, so it has to go and get each part of the metadata. Reading it in with ZAR took less than 1/10 of a second because the metadata is consolidated. Then it's a single line of code to just select a region, calculate a mean, and plot the time series in less than a minute. And to me, like, I think we need to just pause and appreciate, this is a really simple calculation, but changing the time for accessing this data and running a simple analysis like this leaves more time for exploration and science. With the Netcdf example, it takes a lot longer to make this sort of figure. If I was using an older style of maybe Fortran, where I have to actually run through and read each data set, it could take a day or two to do this. And then you're just stuck with that bit of data that you've run, that analysis. Whereas in this ZAR world, I can now decide to run the mean for an adjacent region, or I can bring in a different data set and plot it on top of it to look for connections. And this really changes how we're going to do things. This is enabled by the Python ecosystem. Python has been built on by Jupyter and IPython and NumPy, and then there's more advanced libraries like Xarray and Dask and SciPy, and they're all built on each other and they're interconnected, and they allow us to do science very, very quickly. So we've talked about the data and the software, and now here's a little bit about the compute. These AODs provide the data, but software makes access and analysis more efficient. So this is the example about compute. There are government agencies and commercial-driven solutions for compute, like the multi-mission algorithm analysis platform from NASA. There's ESA's Cloud Toolbox and the Sentinel Hub. And these platforms provide access to cloud deployed data where you're bringing your compute to the cloud. And there's also grassroots solutions with science users who are driving development in this world. And this is an example from the Pangeo community, where all sorts of different scientists are bringing their analyses to the cloud, and it's being adopted very, very strongly by our community, I would say. The Pangeo architecture is to create data stores using an open source software stack and providing interactive analysis using a Jupyter interface, which most users are already familiar with. So whether you're on your local computer and you open up a Jupyter notebook to run an analysis against your own repository, it's the same interface essentially to open up a Jupyter notebook that's on the cloud, accessing data on a cloud deployed data set. So how, as a community of data providers, how can we reduce barriers? And I think it's useful to try and reimagine how our access and data tools can enable transformational science. We want to enable science by publishing these cloud optimized data sets with really useful interactive tutorials so people see how to access and use the data. And as a community, we can increase user interactions and feedback by posting questions on Stack Overflow. And I particularly like this type of interaction because one of the things that I learned on Stack Overflow when I started using it is important questions get upvote, so you often get your answer more quickly. And also, you start to have an interactive community. So it's no longer a forum where there's one or two experts who are giving you their solution. You have the entire community providing solutions. And we can also contribute to open source tools as a community, like intake catalogs or contributing to CMIP6 pre-processing. And this is really powerful when it's amplified across a community. So also, how does minimizing barriers to data then change science? First of all, it levels the playing field for anyone who wants to compute and wants to contribute, because some researchers have built their careers by being the only people with access to the data and the algorithms to process data. And this has impeded progress by restricting who could work on a problem. So here, this is an example on a Raspberry Pi computer that I installed an open source operating system, and I'm able to log onto Pangeo on this $36 computer and run 80 workers and 200 gigabytes worth of data on 2 different clouds. I'm running it both on Amazon Cloud and Google Cloud. And this means that anybody can do science using cloud-based resources without this huge investment in a big computational infrastructure. So we can change how scientists spend their time. And this is this 80-20 slide again. The traditional project requires a lot of time to do this data preparation. And if we can flip that equation by making the data easy to access with no downloading and no cleaning and organizing the data, parallel computing for analysis, we're going to have more time for science. And we're going to advance our understanding of Earth's system. Reproducibility is also important, not just for trust, but also for others to build on your results and advance science further. Reproducibility requires...
Just a quick time check. Just 1 more minute.
Okay, thank you.
Thanks.
Yeah, so this is really important because sharing both code and data in a programming environment builds stronger collaborations and advances sciences faster. So it's not just about sharing the code and tools to create an open space for science. How do we grow it? And as we've seen unfold across the country, closed communities isolate and harm our progress. And open, active communities can advance. They create trust and transparency to work together and to move forward. And science done in an open, transparent manner can go faster if we work together. As a community, we can increase the velocity of science by reducing these barriers to data, demanding open source software, and building out a cloud-based computing science infrastructure. Thank you. And I think maybe hopefully there's time for questions.
There are times for questions. Shell, I should have known that you were gonna nail the timing. You were perfect. Sorry to interrupt you right at the end. I was just like,
it's okay.
I could have kept listening for quite a while longer. I mean, this is such a super story, and there are good questions coming in through the chat. So let's see, where do we want to start? Dave Blodgett asked or said it would be really helpful to see the chunking and compression of the Netcdf source data and similar details for ZAR here. I don't know if you want to respond to that.
Yeah, you know, the part of the chunking is going to influence how quickly I can make that time series data. Here, I actually chunked it in the same way that it was chunked on the internal Netcdf file. So those computations should be pretty similar. The biggest advantage was that all the metadata is pulled out at the beginning. And so that makes reading it initially very much faster. But you can chunk, you know, you can chunk the data in a lot of different ways depending on the type of analysis that you're doing.
Cool, thank you. So there are a bunch of questions that are coming in that I think are going to take more time, Shell. So if you look in the chat, just the last few chats, if there's anything that sticks out to you, Rob Casey has a question, Jeff DLB has a question. So there are.
Yeah, so Jeff asked about non-standard variable names, and I think this is something that we face whether it's in ZAR or in Netcdf, right? We need these standardizations, and you can see even with the CMIP6 data, Julian wrote this pre-processing toolbox because CMIP6 has very specific requirements for their data sets, but those are difficult to enforce. And I know from the ocean data sets, there's the grids. So if you're trying to access data spatially, some are in X and Y, some are in lat and long, some are in latitude and longitude. You know, it goes down to non-standard variable names and also how you're naming your coordinates. And this is an area where coordination through ESIP and other organizations can be really important for making the analysis faster. Robert Casey asked, in the Pangeo diagram, is the data accessed by compute resources? Is it publicly available and exposed? So this is a big question about cloud compute, because you can put data up there and you can egress costs, you know, accessing that data costs money. So in some of the models, like ESA has put up a bunch of SAR data, but you have to pay to access that data. There's other programs like the Google Public Cloud and the Amazon Public Cloud Dataset Program, which is where we have put the MER data. Those public dataset programs are globally available and free. You can download the data, you can move your access, you can move your compute. And so navigating that and understanding, you know, you want to run your compute right next to the data to reduce costs. This is all, it's, you know, it sounds really easy, like let's just move our analysis to the cloud, but there's a lot of details for scientists to learn about that. And I think that's where communities like Pangeo really come in, because you have access to these experts by joining that community who can help you figure out how to make this transition.
Nice. So we'll save the chat for sure, Shell. And one of the things that I've been trying to do is figure out if there's a way for us to have smaller informal conversations with our plenary speakers. So I don't know what your schedule is like, maybe early next week, but maybe we can find a time to bring you back and tech talk with you some more.
Yeah, I'd love to do that. And I do want to highlight, Stephen Diggs made a comment about the $36 computer and bringing the ability to do real science to rural and urban low-income communities. And that's exactly why I showed that slide, because it's a low power device that's so inexpensive and it allows you to do real, and I think this is just really, really neat. I mean, it's great. You can do it you could do these on your cell phone if you wanted. And lots of people have cell phones now, so. Yep.
Yeah, cool. Well, wonderful talk, Shell. And everybody, you can use your reactions to clap and give her a thumbs up. our virtual clapping, lots of clapping for you, Shell. So
thank you.
with that, we're going to move to our next plenary presentation, which is from Julia Stewart-Lowndes, and Christine White, former ESIP president, is going to do our introduction. This is one of our surprises.
Hello, ESIP.
Hey, Christine.
Hello. I'm honored to welcome Dr. Julie Lowndes for her talk this morning. Dr. Lowndes is a marine ecologist, data scientist, and senior fellow at the National Center for Ecological Analysis and Synthesis. As founding director of OpenScapes, created during her Mozilla fellowship, she champions kinder, better science in less time and empowers science teams with skill sets and mindsets for open, reproducible research. She earned her PhD at Stanford University in 2012, studying drivers and impacts of Humboldt squid, the jumbo squid, in a changing climate. Welcome, Julie.
This is Christine. Julie.
Hi, everyone.
We're ready for you to share your screen.
Great. Let me see. Hi, everyone. Thank you so much for that introduction. And I am so happy to be here at ESIP with everyone and meeting you all virtually. Let's see. Is that looking good?
It is looking great.
Thank you. All right. Well, yes, I am so excited to be here with all of you, and I really want to thank ESIP for this plenary invitation and also for leading such an incredible conference. So I am a marine ecologist, as Christine just said, and I actually learned to analyze oceanographic data in around 2008 during my PhD. And that was really through mentorship from colleagues at NOAA and MBARI. So it's especially fun to be here reconnecting with folks right now. But over the last 7 years at NCEAS, I've become a huge champion for open data science, which is how I describe the tooling and the people that are enabling reproducible and transparent and inclusive practices for data analysis. So that's all of you. And this has been so impactful for me that I've actually been moving away from doing my own research so that I can pass forward what I've learned and enable other scientists as a full-time thing. So with support from Mozilla and NCEAS, I developed and run this program called OpenScapes to create more welcoming entryways to this whole world. And I'm excited to tell you about it today. So the problem I'm trying to solve from a scientist perspective is that despite the power of open data science, many scientists are still struggling with data and code, and we're doing this as individuals. And this is because we're rarely trained to work responsibly with data, and we're also not trained to collaborate and work like a team. So this creates a culture where we don't feel confident sharing our data analysis, and we're also not open about our challenges. And this is true even within a research lab that is studying the same study system. And this situation then creates invisible friction when forming data-driven partnerships because people aren't on the same page with what's possible or how they can participate. So this has been a problem for a long time, but it matters now because we're perpetuating these homegrown and non-inclusive practices, and there's no time to waste. And the new wave of scientific leaders who are faculty and lecturers and program managers will not by default lead this transition to open data science because many of them have never seen it or experienced it themselves as a beneficial way to work. And despite wanting better practices for their labs, they feel unqualified and unsupported to establish these on their own. So a contributing solution is to welcome scientists to open data science and empower them with these resilient habits and mindsets, and to do this as teams. So I'll describe this much more throughout the whole talk, but I like to illustrate how it feels to be a scientist in this situation using analogies from Star Wars. So this is Luke Skywalker after he crashed his plane in the swamp of Dagobah. And he's here not able to solve the challenge in front of him with the skill sets that he has. And it's demoralizing and it's lonely. And if you imagine that he attempted to use whatever he had on hand, whatever pulleys or ropes that were in his X-Wing, you know it wouldn't have been reproducible. It wouldn't have been something he was really proud of. and it probably wouldn't have gotten him to where he needed to be on time. But luckily, what happens next is that he meets Yoda. And Yoda uses the Force to solve Luke's problem in a way Luke never imagined was possible. And this is going to open up Luke's whole world because he can learn from Yoda and not only solve his current challenge, but it's going to broaden his mindset to what's possible in the future and the scale of the challenges that he can take on. But Luke didn't go on to defeat the Empire alone. He had a whole community. And this community was super powerful because of its diversity of backgrounds and expertise. And not everybody was a Jedi using the Force, but everyone was contributing in really critical ways to this shared vision that they had. So the Force, to me, is open data science, and its power is manifested not only through the tooling, but through the people that are building, using, and supporting the tools. And I think these two things exist in this beautiful feedback loop, where by using similar tooling, that promotes and streamlines teamwork. And also by thinking like a team, it better equips you to engage in new tools and practices. And because this is a shared mindset that you develop, the idea of team becomes ever broadening and networked, and also your abilities to interoperate and adapt to an evolving software scape also is ever broadening. So an example of this in action is with the Ocean Health Index, where open data science enabled us to do better science in less time and reimagine what was possible for our science. So I've worked with the Ocean Health Index since 2013, and there's a lot to say about it. But what's relevant here is that we combine lots of data, repeat our analyses every year, and we do this as a team. But because we're a team of marine ecologists, we came with varying levels of self-taught analytical experience. But this is what better science in less time looks like for us. Over 4 years, we incrementally introduced the tooling like open source coding into our workflow and established team norms. And it was super powerful for us, but it meant changing the way that we had always worked during our entire careers. And it was really intimidating. We were at that starting point where Luke was when he first crashed, where we couldn't imagine what was possible and we didn't have confidence that we could do it ourselves. But we were able to do it because we had several entryways. For us, the things that benefited us the most were leadership and trust. We had a culture where horizontal leadership, where this enabled a team member who knew the tooling to champion it within our team, and for the rest of us to become comfortable with both the benefits of this new approach and the investment that it required. So we learned from the global R community and established weekly team meetings where we could co-learn together. And this investment paid off, and we had time to focus on new innovation in our science and enable others to work off of our work through these new channels. So the Ocean Health Index R package now supports 20 groups around the world that are tailoring our methods to do data-informed ocean management in their own waters, which was unimaginable with the way we were working previously. But what happens if you don't have an entryway? What if there isn't a champion on your team? Or what if you've taken a carpentries training or are faculty and want to bring these practices to your own group? So I created OpenScapes specifically to be this entryway to open data science for teams and to turn our experience from the Ocean Health Index into a program to meet groups where they are and help them engage. So the cornerstone of OpenScapes is the Champions Program, which provides mentorship for science teams. And it's designed to empower lasting habits and mindsets for resilient culture change and to complement other efforts that are building tools and training individuals. So the core design is that it's team and cohort based to build resilience within and across teams. And importantly, the team leads, like the faculty or program managers, participate along with the other team members so that everyone can see and value what's possible and that the leads can support that horizontal leadership needed to enact it. And this way, everyone can become champions in their own ways, whether that's learning R or whether that's advocating at faculty. A second thing is that open data science is an entryway itself. So by meeting folks where they are and addressing their needs around data analysis, this empowers them and equips them to engage more broadly in open science and other reproducible research practices. And there's a deliberate focus in this program on empathy, inclusion, and kindness. And upcoming, we're also going to focus explicitly on racial justice. So the program is mentored, coached style, and it means that it's not hands-on coding, it's discussion-based. And this is a remote by design program, which also means that participation is through small time investment over longer timeframes. And that is to both reduce the time burden for busy schedules, but also to nurture lasting behavior change. And the lessons that we talk about throughout the program combine the tooling and the people to really develop a shared practices and mindsets within teams and across teams. And that's really to help folks think about research as what is similar across others in their group, rather than what's unique about their study questions. So this program is discussion-based and experience-driven, and we cover topics, like I said, on the tooling side, like how to streamline workflows and interoperate between code and data. And on the people side, we develop a team mindset where we're always collaborating with someone else and thinking about this in terms of future you and future us. And the program architecture is also set up to reinforce what we talk about and to model open behavior. So for example, we take live shared notes in all of our calls using Google Docs, and through that experience, folks get confident contributing openly with others. And the lesson series book and also the OpenScapes website are created and published openly with our Markdown and GitHub. And we talk about how these same tools that we're using for data analysis are also creating a new paradigm for science communication and publishing. And this Zoom gallery of faces here at the bottom, I know this is more common these days, but this is during our inaugural cohort of OpenScapes in 2019, which consisted of 7 different labs across US universities. And these folks are doing such important environmental research, and they are also awesome champions for open data science now. So there's a lot of concrete outcomes from this initial cohort, and it's been exciting to see it continue even now that we're a year past when we finished. But I want to highlight 3 major outcomes from this first cohort, and you'll see it follows the cycle of tooling and people. The first is that they've all created learning communities to learn how to code collaboratively, and this started within their labs. Their homework twice a month was to bring OpenScapes home to the lab and established a dedicated time to talk about open data science within their teams. And it was through these chats that each lab created a new GitHub organization for their labs. And they onboarded everyone in their lab to GitHub through co-creating documentation about lab philosophies, codes of conduct, and also the onboarding process itself to smooth the way for new people joining the lab. And another outcome is that teams have established practices for working remotely, which is a skill in itself. And this is important for modern science under normal conditions, but also is particularly important now as we're all forced to work remotely due to COVID. So these are just 3 examples among many other outcomes, including the collaborations that were formed, the blogs that were written, the coding clubs and new courses that were established, and also the engagement with broader communities through new channels like Twitter and GitHub and meetups and hackathons. And it's all been in the spirit of engaging incrementally while doing our science, but also helping each other and trying to do better. So we were able to reflect on these outcomes and share tips that are more generalizable, along with a 10-week plan for other groups to follow unmentored on their own. And the 3 main tips are to normalize talking about data, and through that to identify and address shared needs, always while thinking ahead for future you and future us. And this builds on the experience of participants who continue to say how much this program has enhanced their work and their science. So these quotes from Malin and Holly really capture what we're trying to do with OpenScapes. And the Champions program had those core design features that I mentioned, but it's also highly tailorable. And the Taylor elements include the timeline, the team composure, and the lessons, among other things that we'll see as it evolves. So since the inaugural cohort, we've also piloted versions with NOAA, Northeast Fisheries Science Center, and with NCs. And it's been really fun to start crafting the different shapes and sizes this program can take. So OpenScapes is in a growth period, and we're prioritizing community engagement and mentoring more teams. And we're also looking for partners. So if you have any ideas of networks that would be interested in OpenScapes mentorship for their teams, please reach out, because I would love to join forces with you. And the Champions program is just one part of OpenScapes' broader vision, which is to do kinder, better science in less time and grow this movement. And we do this by engaging and empowering and amplifying science teams with a goal of increasing the visibility and the value, the practice, and the support for open data science. So I think the ethos of what we're doing here and how we complement existing efforts is captured really well by this quote by Hilary Parker and Roger Pang, who are leaders in the R community and have a podcast about data science that I highly recommend. So they say, if you want to learn to write, you read a lot. And if you want to learn to play music, you listen a lot, but it's hard to do this with data analysis. And they said this in context of why it's important to talk about analyses and be open and share them and build community and culture around these practices so that we can all learn together and be inclusive. And this is really important for building data-driven partnerships of all kinds. So I wanted to close with this illustration just once more about how important the power of welcome is as an entryway to open data science. And as we engage folks in these data-driven partnerships, we can be mindful about welcoming them to engage rather than getting them to engage or making them engage, so that we can have this shared mindset of learning together and making our work as inclusive and effective as possible. So thank you again so much for this opportunity to share about OpenScapes and my work. And I really want to thank my many collaborators and mentors, and additionally saying thank you to Mozilla and NCs. And I'm excited to talk with you all further. So thank you.
Thanks so much, Julie. I think we didn't plan how these talks were going to go together, and they just went so brilliantly together. So thank you so much. One of the questions I'm seeing in the chat is from Rob Casey from Iris, who asked if you could explain more about what the Mozilla style mentoring is.
Yes. This is the open leaders model that Abby Kaboniak-Mays designed. And it is, gosh, where to start? It's the OpenScapes model is built directly off of that model. So it's a remote mentorship program that's led over Zoom with live Google Doc note taking, so that you're hands-on and faces on. And it's taught as cohorts of individuals in the original design, but there is also one-on-one mentorship involved. And this program is able to scale because alumni of the program donate an hour of time a month back to the program to provide that one-on-one mentorship, while the program itself is able to stay kind of as a smaller core team. So yeah, I highly recommend looking into the open leaders model. There's a lot of, they've written a lot of blog posts about it, and the program itself has a lot of spin-offs now too, through their kind of meta program that they designed as well.
Nice. We have time for one more quick question. And I'm curious, we also have a lot of Star Wars fans, Julie, so like the theme of your talk was just perfect. And this is actually our second Star Wars themed talk. So from Daniel Fuca, how do we keep very experienced scientists from hiding on Octu and get them to mentor the Padawan?
Very good. I think it's, I think that it's part of like feeling the benefit of it yourself. Like it feels so awesome to welcome more people into these practices that we love. And so kind of creating that as a norm and having having there be examples of that we can point to sort of help catalyze that behavior in other people. Like, I think leading by example and normalizing that a bit is how we can approach it, and they will follow, I think.
Awesome.
Is that a good?
Yeah. I think it's a great short answer. There's so much more to say there. You should definitely take a look in the chat once you catch your breath. Lots of good, I think, good comments through here on the power of open science and the power of a welcome to. So with that, I think I would invite everybody to use your reaction buttons to clap for Julie. And we are going to move to the second part of our plenary, which is the more interactive part of our plenary. And with that, I'm sharing my screen again. And I'm going to turn it back over to Tamara Ledley.
Okay, thanks a lot. And thank you, Shel and Julia, for some very fascinating and thought-provoking talks. I particularly appreciated it. So as I mentioned at the beginning of this plenary, we are now working to create strategic themes for the next 5 years, 2021 to 2026. The draft themes shown on this slide were developed by the ESIP board following ESIP's organizational evaluation in 2019. ESIP is a community organization, so community input into these themes is vital. During this half of the plenary, we will do some work to crowdsource your input. In addition to gaining valuable input from you, this will also provide another opportunity for our meeting attendees to mix and meet each other. Afterwards, you're invited to join me in the President's Hangout to have further discussion. We will continue to gather community input from clusters through August and September. Plan to present the board with the updated themes at their October meeting and have a final version to be put to a vote by the ESIP Assembly by the January 2021 meeting. So now to start our community discussions on the strategic themes, I will turn over the stage over to Charlie Halley, our facilitator from Backloop Consulting.
Okay, Charlie.
Okay, thank you. Can you stop sharing your screen maybe?
Yep, I can stop sharing my screen.
I think it might be easier if so what I'm going to do is kind of give you the overview of how this next activity is going to work. If everyone could go to the main tab, the tabs at the top of the Kiko chat window, and you'll see one that says 0 main doc. You can look at that with me while I'm explaining how this activity is going to work. Aaron has set up 5, you will see that we have 5 Kiko chat rooms, one related to each of the proposed strategic themes, the new ones. There will be what we're calling 3 walkabouts. So you have the opportunity, I'll give you 3 invitations. So the first invitation will be like, go to the room with the theme that that needs the most reshaping and recrafting in some way for it to be personally compelling and attractive to you. And so everyone will then leave this room and go over to the room that is true for them, most true for them. In that room, you'll have only about 13 minutes to chat with others about, like, what's missing about this? How can we sharpen this? How can we make this better? And then you will type in your responses to that into the room's document. At the end of 13 minutes, you will go to the next invitation, which is go to the theme that you find the most compelling and attractive. And what you're going to do in there is then start saying, why? Why is this one really attractive to me? And what's the steps that we could take to make this a reality? And then the final walk will be to go to the room with a worthy ambition, and it also has the biggest hurdles to cross to make it a reality. And so there you will talk about, like, what are the first steps? What do we really got to do if we really want to advance this theme? So if you scroll down a little bit further, there is an example of the document that will be in each room. So I want you to see this because this is a really cool thing. So after 3 walkabouts to the rooms, each room will have a document with all of your comments, starting with how could we make this a more compelling theme? Even if it's already great, like how could we make it better? And then the next steps, right? So I wanted you to see the big picture of where we're going. And with that, I believe we are ready.
Can I just give maybe just a little bit of tech, make sure that we have the tech set up. So you'll jump down to, and I'll just share my screen quickly so that you know. So the first invitation, Charlie, is what must be reshaped, recrafted in some way before this theme is more compelling and attractive to you. So which one do you think needs the most work is where we want you to go first. So if you look down, you can see the themes and people have started to move. You can already see that. And we're going to ask you to jump down to one of these themes. So I'll say, I think theme 3 is the one that I want to start with. And then we will give you a quick announcement through the Kiko chat interface, and your moderator will be ready to go so that you'll know when to move to the second round, and you'll switch rooms again and join the Zoom for your theme for that room. And then at the very end, after round 3, we'd like you to come back. So that we will quickly wrap up the plenary in this space right at the end at about 12:55. So I think that's all I wanted to say on the tech side. So with that, head to your desired room. And if you're calling in from the phone, the call-in details are right here under the help. So you'll just call in and we won't be streaming. You'll just be watching that on the shared Google Doc. Okay, Charlie, I think I've said it all.
Yep. Thank you so much for adding to that. And this is a time in which if you can turn on your cameras, it's really a lot easier to interact with you if you have your cameras on. So, and if you still have your morning hair and you don't want to turn your camera on, that's okay.
Perfect. Cool. So we will we'll do 3 rounds of this. Each round is about 13 minutes. Is that right, Charlie? And then
yeah,
we will give you a notice. So we'll see you in the rooms.
Erin, I can't remember if you
Meeting, Susan and I will gather input from ESIP sponsors, partners, and ESIP collaboration areas on refining and revising these themes. The ESIP board will approve the draft to share with the Assembly, and we will put those forward to the Assembly for final 30 days of comment in December. At the January Assembly meeting, then they will be adopted. Okay, and then just as a reminder, this is an invitation for you to join us tomorrow, Friday, July 17th from 11:30 a.m. to 2 p.m. Eastern Time for a live networking event that begins with the research showcase, a chance to interact with poster and demo contributors in a fun, fast-paced format, followed by Funding Friday idea development and sketching time. The first Friday event will be a great opportunity to meet others, learn about their research, and seed ideas for future collaboration. And finally, thanks for attending this plenary and for your input on the 2021 to 2026 strategic themes. As we close out this plenary, I mentioned on Tuesday that the ESIP summer meeting is a giant experiment. Following this plenary, our evaluator, David Ryder, will be sending you a short mid-meeting survey. We will use your input to make modifications, provide additional help for guidance, or otherwise clarify things that may have been tricky in terms of the infrastructure. Put your input into this survey. Your input into this survey is important for improving the meeting. So please look out for and complete the survey. Thank you very much and have a good rest of the day.
Thanks, everybody. And if you'll just give us just a few minutes, we will flip the Kiko chat space for the breakout sessions that are happening this afternoon. And so we're heading into about a 50-minute break right now. So thanks so much, guys.
Thank you.
See ya.
Thanks, everybody.
Thank you.
Bye.